Good morning, everyone, and welcome to Module 2, where we begin exploring one of the most important areas in artificial intelligence and machine learning, supervised learning, with a specific focus on regression and classification. In this module, we are moving beyond general discussions of artificial intelligence and entering the practical foundation of how predictive systems actually learn from data. These concepts are central to modern analytics, data science, business intelligence, cybersecurity, finance, healthcare, and countless other domains where organizations rely on data-driven decision making. As we move through this lecture, I want you to think carefully about the difference between systems that simply store information and systems that can learn patterns from historical examples. Supervised learning is fundamentally about learning from labeled examples. In other words, the algorithm is provided with historical observations where both the inputs and the correct outputs are already known. The model studies these examples and attempts to discover relationships that allow it to make predictions on future unseen data. One of the major goals of supervised learning is generalization. A model is not considered useful simply because it memorizes training data. Instead, it must identify meaningful patterns that extend beyond the examples it has already seen. This distinction is extremely important because machine learning systems operate in dynamic environments where future observations may differ from historical data. A successful model must therefore balance learning with adaptability. Within supervised learning, two major categories dominate practical applications: regression and classification. Regression focuses on predicting continuous numerical outcomes. Examples include forecasting sales revenue, estimating housing prices, predicting temperatures, or calculating risk scores. In these situations, the output is numerical and can vary across a continuous range of values. The model attempts to approximate relationships between variables so that changes in input data correspond to changes in predicted numerical outcomes. Classification, on the other hand, focuses on assigning observations to discrete categories. Rather than predicting a continuous number, the system predicts membership within a predefined class. Examples include determining whether an email is spam or not spam, identifying whether a financial transaction is fraudulent or legitimate, or classifying medical images into diagnostic categories. Classification systems attempt to learn boundaries that separate one category from another based on patterns identified in historical data. As we proceed through this module, we will examine how these learning systems operate, how they evaluate performance, and how different algorithms are selected depending on the characteristics of the problem. Some algorithms prioritize interpretability and simplicity, while others prioritize predictive power and the ability to capture highly complex relationships. Understanding these trade-offs is essential because model selection is never purely technical. It is also influenced by organizational goals, regulatory constraints, ethical considerations, and operational requirements. Another important idea we will discuss throughout this module is the relationship between data quality and model quality. Machine learning systems are heavily dependent on the quality, representativeness, and reliability of the training data used during development. Poor data can lead to biased predictions, unstable performance, and weak generalization. This means that the success of supervised learning is not determined solely by the algorithm itself, but also by the structure and integrity of the data environment surrounding the model. You should also understand that machine learning models do not inherently understand context, meaning, or causality in the way humans do. These systems identify statistical relationships and patterns within historical examples. As a result, models can sometimes produce highly accurate predictions while still failing to capture the true underlying causes behind observed behavior. This distinction becomes especially important when machine learning is applied in sensitive areas such as healthcare, criminal justice, hiring, lending, and cybersecurity. By the end of this module, you should have a clear conceptual understanding of supervised learning, the differences between regression and classification, the role of labeled data sets, the importance of model evaluation, and the practical trade-offs associated with selecting machine learning algorithms for real-world use cases. These foundational concepts will support everything we study later in advanced analytics, predictive modeling, and intelligent systems development. Understanding these foundations now will make later technical concepts far easier to analyze and apply responsibly. Let us now begin examining the core principle of supervised learning and the role that labeled data sets play within the machine learning process. Supervised learning is one of the most widely used approaches in artificial intelligence because it provides a structured framework for teaching models how to make predictions using historical examples. At its foundation, supervised learning depends on the availability of labeled data. A labeled dataset contains both the input variables and the corresponding correct outputs, which are often referred to as labels or target values. These labels provide the system with examples of the correct answers during training. The learning process begins by exposing the model to historical observations. Each observation contains a set of input features along with the known output associated with those features. The model studies the relationships between the inputs and outputs in an attempt to identify patterns that can later be generalized to unseen data. The central objective is to learn a mapping function that transforms inputs into predicted outputs as accurately as possible. In essence, the model is attempting to approximate an underlying relationship that exists within the data. An important concept in supervised learning is the idea of ground truth. Ground truth refers to the actual known labels contained in the training dataset. During training, the model generates predictions and compares them against these known correct answers. The difference between the prediction and the actual label is measured using an error function or loss function. The model then adjusts its internal parameters in order to reduce that error over time. Through repeated iterations, the model gradually improves its predictive performance by minimizing discrepancies between predicted outputs and actual labels. This process highlights why labeled datasets are so valuable. Without correct labels, the model has no reliable reference point for determining whether its predictions are accurate. The labels effectively serve as the teaching mechanism that guides the learning process. However, obtaining high-quality labeled data can be expensive, time-consuming, and operationally difficult. In many industries, labeling requires human expertise. For example, medical image labeling may require trained radiologists, while cybersecurity datasets may require security analysts to identify malicious activity manually. Another critical factor influencing supervised learning performance is the quality and representativeness of the training data itself. Machine learning systems are heavily dependent on the data environment used during development. If the training data is incomplete, biased, noisy, or unrepresentative of real-world conditions, the resulting model may perform poorly when deployed. A model trained on narrow or skewed datasets may fail to generalize effectively to new populations, environments, or situations. For example, imagine a fraud detection system trained only on historical transactions from a limited demographic region. If the system is later applied to a different region with different consumer behaviors, purchasing patterns, or transaction structures, the model's performance may deteriorate significantly. This illustrates the importance of representativeness in machine learning datasets. The training data must adequately capture the diversity and variability of the operational environment in which the model will eventually function. Supervised learning is widely used across industries because of its ability to support prediction, estimation, and classification tasks. Organizations rely on supervised learning for applications such as demand forecasting, customer churn prediction, disease diagnosis, credit scoring, spam filtering, recommendation systems, and intrusion detection. In each of these scenarios, historical labeled data enables the model to learn patterns that support future decision making. However, supervised learning also faces ongoing challenges related to changing environments. One important issue is concept drift, which occurs when the statistical properties of data distribution change over time. Relationships that existed historically may no longer remain stable in the future. Consumer behavior changes, cyber attack techniques evolve, economic conditions fluctuate, and operational environments shift continuously. For this reason, supervised learning should not be viewed as a one-time training process. Effective machine learning systems often require continuous monitoring, retraining, validation, and maintenance in order to preserve performance over time. Organizations must therefore treat machine learning as an ongoing operational process rather than a static technological solution. We will now examine the two primary categories of supervised learning problems: regression and classification. Understanding the distinction between these two approaches is essential because they represent fundamentally different predictive tasks. Although both methods rely on labeled data sets and supervised learning principles, they differ significantly in the nature of their outputs, their objectives, and the way model performance is evaluated. Let us begin with regression problems. Regression focuses on predicting continuous numerical values. In other words, the output variable can take on a broad range of possible numerical outcomes, rather than belonging to a fixed category. Regression models estimate how input variables relate to continuous outcomes by identifying mathematical relationships within historical data. The objective is to approximate a function capable of generating accurate numerical predictions for future observations. Examples of regression problems appear across many industries and operational environments. A business may use regression to forecast future sales revenue based on advertising expenditures, market conditions, and historical purchasing patterns. Financial institutions may estimate credit risk scores or property values. Energy companies may predict electricity demand. Weather forecasting systems may estimate temperature changes or rainfall levels. In all of these situations, the outcome being predicted is numerical and continuous rather than categorical. Regression models are designed to identify relationships between variables. These relationships may be simple or highly complex depending on the characteristics of the data. Some regression models assume linear relationships, where changes in one variable correspond proportionally to changes in another variable. Other regression techniques can model nonlinear relationships and interactions among multiple variables simultaneously. The model learns these relationships by analyzing patterns present in historical examples. Classification problems operate differently. Rather than predicting numerical values, classification models assign observations to discrete categories or classes. The purpose of classification is to determine which predefined category best describes a given observation based on learned patterns from historical labeled data. Instead of predicting a number, the model predicts membership within a specific group. Classification applications are extremely common in machine learning systems. Spam detection systems classify emails as either spam or legitimate messages. Fraud detection systems classify transactions as fraudulent or legitimate. Medical diagnostic systems classify patients into diagnostic categories based on symptoms, imaging data, or laboratory results. Cybersecurity intrusion detection systems classify network activity as malicious or benign. In each case, the output belongs to a discrete category rather than a continuous numerical scale. Another major distinction between regression and classification involves model evaluation. Regression models are evaluated based on how closely predicted numerical values match actual observed values. Errors in regression represent the numerical distance between predictions and reality. Smaller deviations generally indicate stronger predictive performance. The objective is to minimize prediction error while maintaining the ability to generalize to unseen data. Classification models are evaluated differently because the outputs are categorical. The focus shifts toward whether the model correctly assigns observations to the appropriate classes. Classification errors occur when the model places an observation into the wrong category. For example, a fraud detection system that incorrectly labels a legitimate transaction as fraudulent generates one type of classification error, while failing to detect an actual fraudulent transaction generates another. The operational consequences of these errors can vary significantly depending on the application domain. It's also important to recognize that classification models frequently produce probabilities associated with class membership. Rather than generating absolute certainty, the model estimates the likelihood that an observation belongs to each possible category. Decision thresholds are then used to determine the final assigned class. This probabilistic structure allows organizations to balance sensitivity, risk tolerance, and operational priorities when deploying classification systems. Although regression and classification differ in their outputs and evaluation methods, they share a common foundation within supervised learning. Both depend on labeled training data, both attempt to learn patterns from historical examples, and both seek to generalize those patterns to future observations. Choosing between regression and classification depends entirely on the nature of the prediction problem being solved. We will now focus specifically on regression models and analyze how they identify relationships between variables. Regression is one of the foundational techniques in supervised learning because it provides a systematic way to study how changes in input variables are associated with changes in continuous outcomes. These models are widely used in predictive analytics, forecasting, scientific research, finance, economics, healthcare, engineering, and business intelligence, because they help organizations estimate future behavior using historical patterns contained within data. At the core of regression analysis is the objective of identifying relationships between independent variables and a dependent outcome variable. Independent variables, often called predictors or features, represent the inputs used by the model. The dependent variable represents the continuous outcome that the model attempts to predict. Regression models study historical observations to determine how variations in the inputs correspond to variations in the output. One of the key strengths of regression is its ability to analyze patterns, trends, correlations, and dependencies within datasets. By examining historical data, regression models attempt to approximate a mathematical function that describes how changes in one or more variables influence the predicted outcome. This process allows the model to generate future predictions by applying learned relationships to new observations that were not present during training. For example, imagine a company attempting to predict future product demand. Historical data may include variables such as advertising expenditures, seasonal trends, pricing strategies, economic indicators, and customer purchasing behavior. A regression model studies how these variables interacted historically with product demand levels. Once the relationships are learned, the organization can use the model to estimate future demand under changing business conditions. Regression models are especially valuable because they often support interpretability. Interpretability refers to the ability to understand how variables contribute to predictions. In many regression techniques, analysts can examine the influence that individual variables exert on the predicted outcome. This characteristic is important because organizations frequently require explanations in addition to predictions. Decision makers often want to understand why the model generated a specific forecast, rather than simply receiving the output itself. Interpretability becomes especially important in areas such as finance, healthcare, public policy, and risk assessment, where transparency and accountability are critical. For example, if a regression model predicts elevated financial risk for a customer, decision makers may need to identify which variables contributed most strongly to that prediction. Healthcare systems may also require interpretable models to explain how patient characteristics influence predicted outcomes. However, it's important to recognize that relationships identified in historical data may not remain stable over time. Regression models rely heavily on the assumption that patterns learned from historical observations will continue into future environments. In real-world systems, this assumption may not always hold. Consumer behavior changes, economic conditions shift, technologies evolve, and operational environments fluctuate continuously. When underlying relationships change, model accuracy may decline significantly. Another important limitation involves the distinction between correlation and causation. Regression models identify statistical relationships between variables, but these relationships do not necessarily represent true causal effects. Two variables may appear strongly associated simply because they are both influenced by an external factor not included in the data set. This means that highly accurate predictions do not automatically imply that the model understands the true causes driving observed behavior. Additionally, relationships between variables are not always simple or linear. Some relationships may involve nonlinear patterns, where changes in one variable produce disproportionately large or small changes in the outcome. Modern regression techniques are capable of modeling increasingly complex relationships, but higher complexity can also reduce interpretability and increase computational demands. As organizations rely more heavily on predictive analytics, regression models continue to play a central role in supporting forecasting, optimization, and strategic decision making. Their ability to quantify relationships between variables makes them valuable tools for understanding historical behavior and estimating future outcomes. We will now examine classification models and evaluate how they make decisions based on learned patterns within data. Classification is one of the most important areas of supervised learning because many real-world problems involve assigning observations into predefined categories rather than predicting continuous numerical values. Classification systems are widely used across industries to support decision making, automation, risk assessment, detection systems, and operational monitoring. At a fundamental level, classification models are designed to assign observations to discrete classes. During training, the model analyzes historical labeled data in order to learn patterns associated with each category. The training dataset contains input variables along with the correct class labels for each observation. By studying these labeled examples, the model gradually identifies relationships that distinguish one class from another. One of the most important concepts in classification is the idea of decision boundaries. Classification models attempt to identify boundaries that separate different categories within the feature space. These boundaries may be simple or highly complex, depending on the algorithm being used and the structure of the data itself. Once the model has learned these boundaries from historical observations, it can apply them to new unseen data in order to determine which category best matches a particular observation. For example, consider a spam detection system. During training, the model analyzes historical emails labeled as either spam or legitimate messages. Over time, the system learns patterns associated with spam behavior, such as suspicious wording, unusual links, sender characteristics, or repetitive message structures. When a new email arrives, the model evaluates the observed patterns and determines which category the message most likely belongs to. Classification models are also heavily used in fraud detection systems. Financial institutions rely on machine learning models to identify transactions that may represent fraudulent activity. The model studies historical transaction records and learns behavioral patterns associated with fraud. Variables such as transaction size, geographic location, purchasing frequency, timing, and device information may all contribute to the classification process. The system then evaluates new transactions in real time to determine whether they appear legitimate or suspicious. Another important characteristic of many classification models is the ability to generate probabilities for class membership. Rather than producing absolute certainty, the model estimates the likelihood that an observation belongs to each possible category. Final decisions are typically based on selecting the class associated with the highest predicted probability. This probabilistic structure allows organizations to adjust decision thresholds according to operational requirements and acceptable risk level. For example, in cybersecurity intrusion detection systems, organizations may choose more aggressive thresholds to detect potential attacks quickly, even if this increases false alarms. In healthcare environments, classification thresholds may be adjusted carefully to reduce the risk of missing serious medical conditions. These examples demonstrate that classification decisions are not purely technical. They are also influenced by risk tolerance, operational priorities, and organizational objectives. Evaluating classification models focuses primarily on how accurately observations are assigned to the correct categories. However, not all classification errors carry the same consequences. Some errors may be relatively minor, while others can have severe operational, financial, legal, or ethical implications. In healthcare, a classification system that incorrectly fails to detect a serious illness may create serious consequences. In finance, failure to identify fraudulent activity can produce financial losses. Another important issue involves interpretability. Some classification models are relatively transparent and allow analysts to understand how decisions are being made. Other models operate more like black boxes, where the internal reasoning behind predictions becomes difficult to explain clearly. As machine learning systems become more complex, organizations often face trade-offs between predictive accuracy and interpretability. Understanding classification models requires recognizing both their strengths and limitations. These systems are powerful because they can identify complex patterns and automate large-scale decision processes. However, their effectiveness depends heavily on data quality, representativeness, appropriate evaluation, and careful operational oversight. We will now compare common supervised learning algorithms based on their use cases, strengths, limitations, and operational characteristics. One of the most important realities in machine learning is that there is no single algorithm that performs best for every problem. Different algorithms are designed for different types of data structures, prediction objectives, computational environments, and organizational requirements. As a result, selecting an appropriate algorithm requires careful evaluation of the specific problem being solved and the operational context in which the model will function. Supervised learning includes a wide range of algorithms capable of supporting both regression and classification tasks. Some algorithms prioritize simplicity and interpretability, while others focus on capturing highly complex patterns within data. This creates important trade-offs between predictive accuracy, transparency, computational efficiency, and ease of deployment. Simpler algorithms are often valued because they support interpretable decision-making. Interpretability refers to the ability to understand how the model reaches its predictions. In many business, healthcare, financial, and policy environments, decision makers require explanations in addition to predictions. Organizations may need to justify automated decisions to regulators, customers, auditors, or internal stakeholders. In these situations, simpler models may be preferred even if they sacrifice some predictive precision. More complex algorithms, however, are often capable of identifying intricate patterns that simpler models cannot easily detect. These algorithms may capture nonlinear relationships, interactions among variables, and subtle dependencies within large datasets. As datasets become larger and more complicated, advanced models can sometimes achieve stronger predictive performance. However, this increased complexity often reduces transparency and interpretability. Algorithm selection therefore depends heavily on the nature of the problem and the characteristics of the data. Some datasets contain relatively straightforward relationships that simpler models can capture effectively. Other datasets involve high dimensionality, nonlinear behavior, or highly variable environments that require more sophisticated approaches. Analysts must evaluate whether the added complexity of advanced models produces meaningful operational benefits relative to the associated costs and risk. Another important consideration involves computational efficiency. Some machine learning algorithms require substantial processing power, memory, and training time. Complex models may demand specialized hardware, large-scale infrastructure, and extensive optimization procedures. Simpler algorithms may train faster, consume fewer resources, and be easier to deploy in operational environments with limited computational capacity. Organizations must therefore balance predictive performance with practical deployment considerations. One of the major risks associated with supervised learning algorithms is overfitting. Overfitting occurs when a model performs extremely well on training data but fails to generalize effectively to new unseen observations. Instead of learning meaningful patterns, the model begins memorizing noise, irregularities, or random fluctuations present in the training dataset. As a result, predictive performance deteriorates when the model encounters real-world data outside the training environment. This issue highlights why strong performance during training does not automatically guarantee operational success. Effective machine learning systems must generalize beyond historical examples. Organizations therefore rely on validation, techniques, testing procedures, and continuous monitoring to evaluate whether models remain reliable after deployment. Preventing overfitting is a central challenge in machine learning because highly complex algorithms are often vulnerable to memorizing training data. Trade-offs between predictive accuracy, interpretability, and efficiency are present in nearly every machine learning project. Highly complex models may achieve impressive accuracy, but remain difficult to explain to decision makers or regulators. Simpler models may be easier to interpret and deploy, but may produce less precise predictions. Selecting an appropriate algorithm therefore requires balancing technical performance with organizational priorities, legal requirements, ethical considerations, and operational constraints. Ultimately, machine learning algorithm selection is not purely about maximizing accuracy. It involves understanding the strengths and limitations of different approaches and determining which model best aligns with the specific use case. Successful supervised learning requires thoughtful evaluation of data quality, model complexity, interpretability, scalability, and maintainability.